Hello everyone, welcome back. So in our last class we have discussed about semiconductors, and in that discussion we have gone through various materials like inductors, semiconductors and insulators, and we have also gone through the crystalline structure. And in the discussion of crystalline structure we have continued our discussion to energy band theory of crystals, that how the energy bands are being formed. Then we have moved forward to energy band structures for different materials, and then in that energy band structure we have also gone through the Fermi Dirac function. So today we are going to discuss about the carrier concentration. So carrier concentration of an semiconductor. So to start with, first we will see the carrier concentration in case of a intrinsic semiconductors. Then we will be moving forward to the carrier concentration in extrinsic semiconductors. So to start with intrinsic semiconductors, what we have is, for the determination of conductivity of a semiconductor, so it is essential to know the concentration of free electrons in the conduction band and the concentration of holes in the valence band, right? So the identify the number of electrons in the conduction band, so it can be identified by the product of the number of existing states at any energy level E, and the probability of its occupancy gives the population of the occupied state by an electron. So the electron population can be found by the number of conduction of electrons dn per cubic meter at any energy level, which is defined as this function. So now here we have the value of Ne is the density of states and Fe is the Fermi function, and they are defined by these two equations which we have already found in our last class. Now here the value of the density of electron is given by this formula, which is considered as the derivation of the above equation is based on the assumption that the bottom of the conduction band is a zero potential. But in case of semiconductor, the lowest energy of the conduction band is EC. Therefore, the equation of Ne will be modified into this format, right? So now similarly, if we consider E is very much greater than EC and E minus EF is very much greater than KT, then the Fermi Dirac probability can also be given as this function, where this one term will be neglected and it will be coming to the numerator. So this will be the function. Now if you put this with respect to the concentration of electrons, so the concentration of electron in the conduction band is given by integration of NeFeDe, where now if we put the value of NeFe here, then we will be finding it as this, where this is the value of Ne and this is the value of Fe. Now what we found here is the value of gamma is given by this equation or this value. So we'll use it later on. So for the time being, let us see how this equation turns out to a particular format. So now moving on, so if we consider E minus EC is given by KT into X, then this function will be given by this format, where as we can see here, this E minus EC is converted to KTX to the power half. Then this E minus EF is converted using this formula. So from here E will be equals to EC plus KT into X. So that is what is written here. Remaining is minus EF by KT, right? Then this KT dx is the output of, if we do differentiation of uh, KT x, this will be KT will be constant and remaining will be dx. So this is KT dx. Now moving forward, so this term is a constant term KT, so that will be coming out. So this term will be coming out here. KT will be coming out to the power half. Then this KT term will also come out. So this is KT here. Then e to the power minus of EC minus EF by KT. This term will also be a constant. So that is why it is out of the integration. and gamma is also constant, so gamma is also out. So the remaining part which is inside the integration will be e to the power minus x, because kt and kt will get cancelled, so remaining is e to the power minus x, and from this term we are getting x to the power half. So x to the power half and e to the power minus x will remain inside the integration, right? So now moving forward, this kt and this kt combining together will be 3 by 2. Then this is the e to the power ec minus ef term. This is the gamma term. Then the remaining term that is inside the integration. So now if you consider e to the power half and e to the power minus x dx, this integration term to be replaced by this root over pi by 2, then this equation will become something of this format, where this is kt, this is remaining term, this is the value of gamma we have written here, and this value is root over pi by 2. So now here pi root over pi and root over pi will get cancelled, and this 2 will cancel with this 4, keeping the value as 2. So this will be the remaining output. So now if you consider this whole term is given by nc, then the equation of this carrier concentration in case of electrons, that is the intrinsic semiconductor, what we have is n equals to nc into e to the power ec minus ef by kt. So this is considered as the carrier concentration of intrinsic semiconductor when we have electrons, where nc is the effective mass of a free electron. Now similarly, if we continue, we can have the value of p given as nv e to the power ef minus ev to ev. Ev is the maximum value of the valence band, maximum energy level that can be attained in the valence band is ev, so by kt. So these are the carrier concentration of an intrinsic semiconductor. So now if case of intrinsic semiconductor, as we know, number of electrons is equal to number of holes. So if you compute that, so both the terms will be equal. So after this, if we bring this nc and v term over here equals to, then remaining e to the power term on the other side, then this will be e to the power ef minus ev by kt, that divided by, so this term will become, if I bring it up, this will be ec minus ef divided by kt, right? So now if we take log on both sides, this will be ln of nc by nv equals to ln of e to the power, after combining this we'll have ec plus ev minus 2 times of ef divided by kt. Okay, so now on left hand side we have this term, and on right hand side this logarithm will get cancelled and the exponential term, and we have ec plus ev minus 2ef divided by kt. Now if I bring this kt term on left hand side, and this will be ec plus ev minus of 2ef equals to kt ln nc by nv. Okay, so from here if I determine the value of ef will be given as ec plus ev divided by 2 then minus of kT by 2 ln Nc by Nv. Now, as we know, in case of intrinsic semiconductor, the value of Nc equals to Nv. So what we have here is EF will become, this term will get equalized to 0 because ln of 1 is 0. So what is left is EC plus EV divided by 2. That means in case of intrinsic semiconductor, the Fermi level lies in the middle, which means this is the conduction band, this is the valence band. So the EF will lie in the middle, where we have this is EC and this is our EV. Okay, so this is the Fermi level in case of intrinsic semiconductor. So now moving forward to extrinsic semiconductor, if you see, then the Fermi level will be given by EC minus KT ln NC by ND, where ND will be given by this expression NC e to the power minus AC minus AF divided by KT, which is the concentration of the donor atom. And similarly, Fermi level of p-type material is given by EF equals to EB plus KT ln NC by NA, where Na is Nv e to the power minus of EF minus EB divided by KT, which is the concentration of acceptor atoms. Okay, so now, which means, as we can see here from the diagram, in case of the intrinsic semiconductor, we have the Fermi level in the middle. Now in case of n-type semiconductor, what will happen? This Fermi level will slightly move up because we are doping the semiconductor with more number of electrons. So whenever doping them with more number of electrons, then the affinity of EC will be slightly moving down to a value of ED, so that the affinity of electrons to move towards the conduction band increases and the region of EC changes to ED, and at the same time the Fermi level will go up because the electron will have more affinity to move towards the conduction band. Now the case will be totally opposite when we consider p-type semiconductor, where the Fermi level will come down as the valence band will move up to this range, as we can see here, which is given by EA, and due to which the reducing the number of electrons and increasing the number of holes, the affinity of electrons to move towards the conduction band will decrease. So that is why the Fermi level will shift down. Now this curve line, as we can see in all these three cases, represents the effect of temperature. So when we increase the temperature, then the Fermi level will tend to move upward towards the conduction band, so which is only showed here. So this is the Fermi level in a semiconductor, considering the intrinsic semiconductor and the extrinsic semiconductor in case of n-type and p-type. So I hope you have understood this. So now let us move into a numerical. So for a particular semiconductor, the effective mass of electron is given by the value 1.4, and if EC minus EF is 0.25 electron volts, then determine the effective density of the states in the conduction band and the concentration of electrons in the semiconductor at two values. First one is for 300 degree Kelvin and second one is at 400 degree Kelvin. Here we have, as we already know, value of Nc is given by 2 times of, as per the formula, it is 2 pi mn kT by h square whole to the power 3 by 2, and the value 1.62 into 10 to the power minus 19 to 3 by 2. Right, now here we have the values of m given, h is given, k is given. So if you put them here in this equation, so we'll find out the value to be, I'm directly writing the value. So 4.15 into 10 to the power 25. Okay. Now the concentration of the electron, to determine the concentration of electron in the semiconductor is given as n equals to nc e to the power minus of ec minus ef divided by kt, right? So now this will be the value of nc we have already obtained, 4.15 into 10 to the power 25, then e to the power, this value ec minus ef is already given, which is 0.25 electron volts divided by kT. The value of kT will be computed using 300 degree Kelvin, and the value of K, which will be coming out as 0.0259. So after equating the values, we'll have, this will be 2.67 into 10 to the power 21. Okay, so this is the answer for 300 degree Kelvin. Now moving forward, for 400 degree Kelvin, what we have to do, we have to consider the, determine the value of NC like this. So the value of T here initially was 300 degree Kelvin, so now we'll be putting the value of T as 400 degree Kelvin, and for the second part, if you do the calculation in the similar way, the value of NC will be coming out as 6.38 into 10 to the power 25, and the value of n in the same way, if we calculate, it will come as 4.1 into 10 to the power 21. So now just go through the numerical and see whether you are getting the answer or not. So this is as simple as that. So now moving to the next question, it is given here that in an n-type semiconductor, the Fermi level is 0.3 electron volt below the conduction level at a room temperature of 300 degree Kelvin. So if the temperature is increased to 360 degree Kelvin, determine the new position of the Fermi level. So as we know, the Fermi level equation of an n-type semiconductor is given by EF equals to EC minus KT ln NC ND, right? So we have found this in today's class. So therefore EC minus EF will be KT ln NC by ND. Okay, so as it is given at 300 degree Kelvin, this value is 0.3 electron volts. So this is equals to 300 degree Kelvin into K ln of NC and D. Now considering the second case, where we have EC minus new Fermi level equals to the value of the temperature is 360 degree Kelvin, and this is K, then ln again NC by ND. Now if we take the ratio, then we'll simply get the value of new Fermi level, that is EC minus EF1 will be equals to 360 divided by 300 multiplied by 0.3. So it is as simple as that. So the value will be coming out as 0.36 electron volts. Okay, so this is the answer. So you can write this type of numericals for uh, this topic, and we can continue our learning further. So now moving to the next topic for today, which is known as the work function. So let us consider this is the energy possessed by an electron, and this is the energy which is required to move outside the metal. That means if a electron wants to move outside a metal, then it has to possess energy more than this. So now this energy is given by EW. Sorry, this is a mistake. So this energy is EB, and the maximum energy possessed by electron, as we know, is EF. So the work function is said like that: the extra amount of energy which is required to move outside a metal will be given as EW equals to given by maximum value or the maximum energy required to move outside the metal and the energy obtained by the electron. So the extra amount of energy it will require to move outside the metal is known as the work function. Okay, so that will be all for today. So today we have discussed about the carrier concentration of intrinsic and extrinsic semiconductor, and we have seen few numericals, and then finally we have discussed about work function. So that will be all for today. So till then, keep learning. Thank you for joining.